let's press on with example 21. So to answer the question, whether or not it has a vertical asymptote at x equals to 3, what do? We therefore have to check how the graph or the function behaves near x equals to 3. So we have to do this thing. We have to find the limit when x approaches, say in this case like 3 from the left. So we can do x squared minus 16 over x minus 3, x minus 4. Now, someone in the class say, why do I need to check the left side after the right side? If you are talking about asymptotes, it might be a good idea to check the two sides separately. Okay, so limit. Okay, then you know that you can actually do some factorization and cancellation. Upon factorizing and cancelling, what do you have? You will have with x plus 4 on the numerator and then x minus 3 on the denominator. Okay, so when x goes towards 3 minus, so think of a number that is considered 3 minus is 2.99. So then you will realize that the numerator will be positive, and then the denominator is actually negative and small. Right? That being the case, right, the resulting limit will therefore be a negative infinity. Okay? Graphically, right, you know how it is going to look like. Graphically, it's going to look like this. That when x is on the left of 3, what it merely means is when on the left of 3, the graph looks like this. Oops. You know, I'm using PDF, I find the PDF version to write is nice. So, yes?
So like how do we present this when we ask to do a question?
For this particular one, right?
The positive and negative part, how do we present it?
Like that?
Just like that?
Do you have a suggestion?
No, it's just a question.
Oh, yeah, it's like that. Yeah. Okay. So, because we are checking for the asymptote, actually, if you are just to ask to find the limit, right? Actually, you don't really do left and right for a function that is defined the same on both sides. But for this case, because you're looking for asymptote, I just thought that maybe a good idea to check the left and right asymptote separately. Nothing stops you from doing it without checking left and right. You can just do it, x goes to 3 without having to check the left or right. You can do it. For this question, you could have the option. But if you do not want and you prefer to do like what I've done for checking for asymptotes, then
why need to check both though?
You don't have to. Just that I just want to show you both.
You can do it now.
Right. You don't have to do both, no. Yeah. So Kenneth is giving a suggestion that actually why do you need to do both? Because
it's
if you got it's true for one side is good enough. Yeah, he is right, so then this one in this case, right? You're going to get in this case when x goes towards 3 plus. When x goes with 3 plus, the numerator is how much? Okay, I'm not sure what happened. It pops up. Okay. So when x goes to 3 plus, the numerator is positive, and this is going to be positive and small. So therefore, this gives you a positive infinity. And then graphically, you might want to imagine how it looks like. It looks like this. This is at point 3. Okay. Then now we are keen to see what is it like at the point 4. Okay. So the question asked is, does G have a, okay, so now you're going to do the same thing now. You're going to look at the limit when x goes towards 4 from the left, the function becomes like that, you know. Okay, I think I should not jump step. I should not jump step. Bad choice. Bad choice. Okay, I'm going to do the same thing. And this x squared minus 16, and then this is x minus 3, x minus 4, and then upon factorizing and cancelling, you get x goes towards 4 minus, and then you can get x plus 4 over x minus 3, and that gives you 8. Then you try the other side and see what happens. X minus 3, x minus 4, that gives you, you need a fan or something? 8. Right. So in this case, right, does it have a asymptote at x equals 4? The answer is no, right? And then graphically, how does it look like? Say at the point x equals to 4, the calculation tells me that the limit on the left and on the right is 8. So I'm going to mark down a value 8. But I do know that the function which is like this, right? The function which is like this cannot take the value 4, which means at 4 it is actually undefined, right? And if now I put in more substance to this portion of the graph probably looks something like this, near 4. Right, it looks like this. Okay, so this is a case where the limit exists, but the function value is undefined over there. Okay, let's press on. Okay, someone still jotting down. It's very good, right? We can actually record all our lessons, you know. I was successful yesterday, so I uploaded one and I posted it. I sent the link to one of your classmates. I posted it on YouTube. I find it easier YouTube instead of the schools that one drive. You know, one drive is quite troublesome. YouTube, yeah.
Also, can you put it on Microsoft Stream?
Okay.
Because the benefit of that.
Yeah, you don't have to download the file, is it?
No, it generates subtitles.
Oh, generate subtitles. As in, I record it using Stream, is it?
No, Microsoft Stream just allows you to upload video files.
Yeah.
And then when you upload them, it generate subtitles for you.
Automatically, yeah.
Yes.
Wow. But that's provided I can pronounce all the words correctly. You know. I've seen it before. Yeah,
All the words are English.
Yeah, I think that it's quite scary. You know, sometimes some of the word that I mispronounce, it comes out wrong. Can we stay to YouTube? That's more familiar with YouTube now. Let's use YouTube now. Or you can view on the phone. Sorry about it. I'm not familiar with Microsoft Stream, but I do know that when I use the PowerPoint, when I speak and present, right? Present, speak.
Subtitle.
It goes wrong. The subtitle goes very wrong, you know. Yeah.
The very entertaining one.
Okay, so pardon me lah. So let me use YouTube for a moment until one day I take the bold step to go into Microsoft Stream after I brush up on my language. You know. Yeah, Okay. Okay, then the next one. This is actually an MCQ question in example 22. A show of hands who have already attempted this question apart from Kenneth. Kenneth has done everything, huh? Okay. Oh, good. So you're done. Okay. So that being the case, you can go a bit quicker. So in this question, right? In this question, example 22, you're asked for whether or not the statements are true. To start with, how do you know that this is false? This is false because this diagram shows you a function. Why is this diagram a function? Because
1x to 1y.
because okay, 1x to 1y. Okay, 1x to
1x to some y. Then one x only points to 1y.
1x points to 1y lah. I think it's right. So 1x points to 1y.
Y can repeat.
Yeah.
Explain that.
Yeah, you're right. Actually, what you described is correct. But what we typically would do is to use what's called a vertical line test. Because every vertical line that you draw cuts the curve at most once, we therefore conclude that this is actually a function. For that matter, is circle strictly a function? Circle is not.
If a circle is infinitely large, maybe, but no.
Okay, the next thing is, it asks you the limit at x as x goes towards 0, is it equal to 1? No, right? Because in this case, the left limit is 1 and then the right limit is undefined. So for that reason, this is wrong. And this one, there's a small print, in the part D. Okay, now part C is the limit at x equals 2 for the same reason like part B. This one don't have. You have two different limits. And then for part D, towards 2 plus, it means coming from the side of 2, the limit is really 3. And then it says about the left limit at 2 is undefined. That's not true because the left limit at x equals 2 is actually equals 2, see? So for the reason, I am very sure for those who tried, you have picked D as the answer. Caitlin, what do you pick? What do you pick? What choice do you pick?
What I pick?
What did you choose?
E.
Donkey, right? Great. Okay, let's do our quick check. Okay, you're told that the limit. Okay, so in this quick check, do you think that this is mandatory true? The FA must be equals to L? We don't have to, right? Because you can draw a simple diagram to show that while the limit exists,
Point does not.
yeah, the point may not have a value. So this therefore is, and then do you think that FA is not equals to L?
No.
Right, if you have a diagram that's like that,
Let's draw a straight line.
right, straight line, a nice curve, nice curve,
E for x function.
right, this B. So in this case, right, FA is equals to the limiting value. So therefore, this is therefore wrong. So for part C says that if this is true, then it says that fx can't be L. This is not true because you can also draw.
You don't have to draw a.
Yeah, the other diagram will work right now.
Yeah, the
Right.
initial diagram just works already.
Or I can just do like that. Okay, let me call some L. Right. So it is possible for f of x to be equal to L for some numbers x. So that being the case, right? Therefore, D is the answer. Is none of the above. Okay. At this point, we have covered quite a lot about limits. In this chapter, the first half is about limits, and the second half is about
Continuity.
It might sound complicated, but it's not. It's a very straightforward concept. It means not broken. Not broken. So if you say that a function is continuous at a point, it basically means it is not broken. I am sure drawing this graph, you understood, you will understand what I mean, you know, that the function is continuous and it's obvious. However, you can't do it in this module and say, hey, function f is continuous at x equals to a by looking at the graph, and it's so obvious. You can't do that. In math, using a diagram to just prove your case, it's not robust enough. You know, we prefer. What do you prefer? Instead of using diagram to, we need analytical proof. That means by calculation. So therefore, to prove that a function is continuous at a point, you cannot just say, please refer to the diagram, and it's obvious, cannot. You have to prove three things. What are the three things?
The limit exists, the point is defined, and the limit equals to the point.
And then you look at the three conditions again, you look again, and you look again, and then, hey, Mr. Lim, couldn't this covers 1 and 2?
Yes.
Technically, yes.
Okay.
Technically, yes. Because with this statement, this one must exist, and this one must exist really.
Yeah.
However, in AP syllabus and in our curriculum here, if you are asked to prove that something or function is continuous at that point, we need you to do these three steps. No? Step 1, step 2, and then you marry the two of them together in step 3 and make your conclusion. You have to do it this way. Okay? So what I mean by this, okay, we'll see in a later example, but for now, okay, we are going to judge things from the diagram for now. Okay, for now. Okay. Okay, like in this diagram, okay, we can't do it by analytical calculation because you don't have enough information on a function. So that's why for this example, we're going to do it from the diagram. It asks, is condition 1 fulfilled for the point x equals to a? Yes. Right? Yes, right? Because at the point A, f of A is equals to a defined value as seen in the diagram. So what's the value? The value is somewhere here. This is your FA. Next, is condition 2 fulfilled that the limit exists? Yes, the limit exists, right? Because the left limit and the right limit are the same, so the limit exists. Thirdly, is the limit value, the limit is equal to the value of the function at the point? And the answer is yes. And because you have 3 yeses now, on the 4th one, you get the, you know in AGT, the judges like to say, you know AGT? Those who have watched, you have 4 yeses, they declare that, and then the contestant feel thrilled by it, and they're very happy. Who don't watch AGT?
Or BGT.
AGT or BGT, you watch? Don't.
I don't watch TV.
Oh, you know, YouTube is on YouTube. Actually, I watch on YouTube.
Yeah, it's also on YouTube.
Oh,
Yeah.
okay. I just don't watch it.
It's a very entertaining program, that you want to go and watch it because
Simon Cowell.
I'm quite impressed by the determination and the hard work the people have put in. I watch a lot of this with my daughter, and it's quite fun to comment about the performances. And apparently, my daughter had fun. She liked those instances where the performers do badly, and then the judges are sometimes condemn them. Then she laugh over it. The performers perform in front of judges, right? Then judges give comment. For those not so good ones, some of the judges are very, quite unpleasant. You just tell them straight on the face. Yeah. Okay, in any case, we have 4 yeses for A. So for now, I like to give yourself that I think you need about 30 seconds, okay, to fill in B, C, D, E. Okay, now fill in B, C, D, E on your own. Let me compare. Have I already told you that we are going to have a graded task 1 on the 27th of January?
Huh? What?
Oh, okay. We are going to have graded task 1 on the 27th of January.
You haven't told us which week's the.
Okay, 27th January is the Friday immediately after the Chinese New Year.
No, that's
And the
not
coverage is from page 1 to 21 of chapter 1.
21 is under continuity.
Yeah, under continuity. Okay, can you fill in the table? Yeah, let me compare. So for those who have done, you can look up and compare. For those who have not, you want to try first. No? Then you finish it. Good. Martin. Where's Martin?
No! Okay, green.
Huh?
Green.
Green. You finish already? Yes, correct, all correct. Okay.
Green, at least it's consistent.
Yeah, constantly wrong because in that class, that Martin.
Consistently wrong.
Is that Martin here?
No.
Or then in that class again?
The other class.
O2, Martin. Because Martin, I think, sits around there also. Yeah.
The error is still consistent.
In this class, you all are seated separately, you know. In
No,
O2,
haven't yet. We haven't.
decided on the sitting arrangement.
Yeah.
Okay, this is good. This is good. Your own space. Well, Tyler, you like this arrangement?
But I think our Mr. Lim will back to differ.
Yeah, that's Mr. Lim Chongchen, right?
Yeah. Mr. Lim will probably back to differ.
Okay. Anybody has any questions about the yes, no here? Anyone has a different opinions? Okay. If you don't have, yeah, good. Let me press on. Okay. Now is the time for us to do a question to test continuity, to check for continuity, using the 3 steps, you know. And you really have to go through the 3 steps, no? So, step 1, what must you do? You must calculate f of 0 at the point in question. Based on the definition, f0 is equals to, you know what? I actually prefer that you write this intermediate line, no? So that I know that you know. So that I know that you're using the right one. And the whole world knows that sine 0 is...
Why?
Sine 0 is 1. Okay.
That's 0.
Then secondly, we want to look for the limits. And to do this one, because the function is defined differently on either side of 0, you therefore have to find the limit separately. So maybe you want to do a 2a here. 2a. Limit as x goes towards 0 minus of fx. And this will be equals to limit x goes towards 0 minus sine x. You must be very patient to write the same thing again and again. 1. Then you might have a say 2b. That's going to be limit x goes towards 0 plus, in this case is x plus 1, and it goes to 1. So you say therefore this is equals to 1 by 2a and 2b. Then number 3, you establish that limit as x goes with 0 is equals to 1 and it's equals to f of 0. And say therefore by and 3 f is continuous at x equals to 0. This is the expectation, you know. It may look too trivial, too straightforward, but you just have to do it this way. Okay? Can I? Okay, pressing on, we now have example 25. Okay, in example 25, you are given a condition that the function is, okay, wait, before I go on, you're finished copying? Okay. Example 25, you are given a condition that the function is continuous at x equals to 1. Because of this continuity, we therefore can say that f of 1 must be equals to this limit. And you realize that this is exactly the third condition of the 3. So the third condition of the 3 actually encompasses everybody. Right? So the moment you know that a function is continuous at a point, this is the consequence. And then it will say that at x equals 1, this therefore is c. And now you have to find the limit when x goes towards 1 of this function. Okay, let's hear from Wen Kai. I know, I got it this time. This is Wen Kai, the boy. I know. It doesn't need to pretend now. What do I do from here, Wen Kai? Okay, Wen Kai gesture to me that we need to do this, right? Telepathy, okay?
Oh,
We use the
telepathic.
conjugate, okay? Conjugate, and then this gives me limit x goes towards 1. Okay, now has to be Kai Winston. What's the resulting fraction?
Don't say anything, I'll use telepathy.
Right. And she said, no. Not this. She didn't say this. She said this. She said wrong thing. Right, she said this. If you were to multiply the numerators, you find that after multiplying the numerators, right,
You get x minus 1.
you actually have a nice cancellation, you know. Let me do it for you. This one, when it times together, this whole thing cancels very well with this one. And then this gives you 1 over 4. This is how we can find the value of C. Okay. Then moving on, right? We are going to look into common functions which are continuous. Okay, over here it listed for you a list of functions which are known to be continuous. Meaning to say, if you ever have to make reference to a sine function, it is taken for granted that that is a continuous function. Or your function given to you is a polynomial. Be very careful, no? Polynomial, right? The powers of x, right, must be integers starting from 0. You It means in x power 5, x power 6, x power 7, you cannot have x power of negative 1, you know. Then that won't be a polynomial anymore. To be a polynomial, it must be of this form. Okay, and then it must end. Interestingly, if it ends somewhere, it is called a polynomial. If it goes on forever, let me say if like that, is it still a polynomial? If it goes on forever, the answer is no, no. What is it called? If this thing goes on forever, that means, you see, a polynomial must stop somewhere. Must stop, you know, must stop. If it go on forever and doesn't stop, what do you call it?
Infinite series.
I know it's an infinite series, but it's a proper name for it. Okay, give it suspense. It's called a power series. Yeah, power series. And then the next box gives you a definition. To be continuous on an open interval, it's quite easy. It means it is continuous at every point in the open interval. Full stop. To be continuous on an open interval. Earlier on, we talked about continuity at a point. Now we extend the idea to continuity on an interval. In particular, we are talking about continuity on an open interval. You know, this open and close can be confusing. No, you'll see it later. But in the meantime, for open interval, I want you to know that it's quite easy. Okay, quite clear. Right, so there are some examples about functions being continuous on open intervals. These are examples. The difficulty lies in talking about continuity on a closed interval. If you now look into the next box, okay, on the next page, you realize that it is more elaborate as compared to the case of continuity on an open interval. Why? This is because for closed interval, the endpoints has an issue, no? So for continuity on the closed interval, the limit at the endpoint is only a one-sided limit. You just need the one-sided limit to be equal to the function value at the point. You know what I mean? Remember, talk about continuity at the point, we always have three conditions, right? And the one of the condition is the two-sided limit must be equal to the function value. But in the case of continuity on a closed interval and at the endpoints, you want to note these two. Okay? Because at the endpoints, you only have one-sided limit to talk about. Okay, then when I show this example, right? I show this remark, right? And then the example. Some people ask this question, you know. They say, is there something wrong here? Some people ask, hey, is there something wrong in this statement? And the way to see is like this, no? Let me ask you, what is the complement of this interval?
Of the open interval, negative infinity to 0.
Right. Because the complement of this interval is, the complement is open, right? Yeah. Therefore, this is considered as closed. This is one way of seeing it. There are some people.
This is why people say the real number series is both open and a closed set.
Right.
Because the complement is open, which is why it can be closed.
So it's a confusing thing, you know. So this last one, okay, you want to know that it's considered to be a closed interval because the complement is open. See me?
The definition is that the complement of an open.
This is an open interval, so implies that this is closed.
That's funny, not gonna lie.
Yeah. So things touching on infinity can be confusing, you know. I told before, like this one, it's not too bad, you know. You will agree. But this one is a bit confusing, you know. Right. So I think maybe we haven't have enough knowledge of the number system. As I told you, maybe it's flawed, you know, to start with. And if you do come up with good ideas, tell me first. No? Okay, let's move on. Okay, now the question asked is, okay, in this diagram, it asks you, is the function continuous from the left of b here? From the left of b, the left limit, right? The left limit when x goes towards b minus of the function is equals to the function value at b. So therefore, this is correct. This is continuous from the left at b. Is it continuous from the right of b? This one is no, you know, because from the right of b, the limit is different from the function value. Talking about noise, lately my daughter told me, you know, she always sleep at 1 p.m. at 1 a.m. 1 a.m. I say, why? I always see you going to bed about 10 plus. She say, no, because the street cars are always going past that same major road. Because we shifted not too long ago, so she told me recent time she cannot sleep, you know, the car's noise. No? Then I said, then why you can sleep at 1? She said, thanks for the simulation. She said at 1 a.m. right, the car stops already. Then she can sleep, you know. Some people just love to live in areas that's absolutely quiet. No? Personally, I cannot. No? I like to live in city center. I cannot live in a place that's like, no lighting, no this, no that, no shopping mall. No, I cannot. I'll die. No? I must live in very vibrant place with a lot of people, a lot of happenings. You know, then I find it very happy. You know. I'm not sure. But most people I ask, they want to buy a house far away from everybody else and then happily live in there, you know, and of course they'll do their daily life by driving here and there to get things. But I don't like, no. I like a shopping mall to be at my doorstep. I like everything else to be, you know, nearby, you know, and a lot of happenings around. Okay, back to math. So the question is f continuous on the closed interval? Let the class echo. Okay, only 2 yeses. Yeah, on the closed interval, it is indeed. Okay, moving on. Okay, from a given function which is continuous, we want to ask some simple questions. If we derive a new function from a continuous function, would the new function be continuous? For example, okay, you read the statement. If you look in the mirror, we all know, right? The function and its inverse are mirror images. Image line? Y equals x. Okay, y equals x. Okay? So if you look in the mirror, do you see a different you? Different person?
Oh god.
If you look in the mirror, you should see yourself. You see yourself. You don't know? Wait, different person. Okay.
Are we going to get down to the philosophy of what is real, what is not?
So a function when reflected in the line y equals x to give the inverse, if the function is continuous, so is the inverse. It's natural, right? Okay. So therefore this box tells you that the inverse will also be continuous. You know, this one, and this one. Okay, let's read this one correctly. What is this? It's called the reciprocal.
Yeah.
This is called inverse. Many people are confused with this. No? They think that reciprocal and inverse are the same. They are confused because in the case of numbers, the inverse
is the reciprocal.
Yeah, only true in numbers, no. Lo and behold, do you know that there isn't such a thing? 没有 don't have.
The question of whether it's inverse the sign.
No, don't have.
Or
You cannot
square
like that.
the
You cannot like that. Don't have. No such things. No. You can only write at best this. If you really need to,
Square the entire.
yeah, you got to write the brackets and then. Okay. Now the question I ask you is, if a function is continuous, would the reciprocal also be continuous?
No.
Maybe only, right?
Maybe, yeah.
Maybe. Okay. All right. So now in example 28, also 26, you want to ask, and the way to address this question is because, and these two, how are they related? Why are they rated? Because you look like restless, you were moving. So give it a chance. You're not ADHD, right? You know it's ADHD, no? People who cannot sit still, no?
What are you referring to, by the way?
Kai Wen. Kai Wen, what is the relationship between the function f and g in this case? They are inverse of each other. The inverse of fx is actually, in this case, this is actually inverse x now. You look carefully, right?
Yeah.
And now, because this is continuous, we can then use the earlier result to say, therefore, the inverse is also continuous. Good, right? If you look in the mirror, you don't change your shape, you look the same. Right? Okay, let's move on. Okay, give yourself the chance to write down this follow. Okay, it's good to do some writing. Everybody on it. After my lesson is
Honest.
still lesson
Honest.
What honors?
Not directly, but not directly. Huh?
Back to back. So must very hungry by now.
I feel bad for you guys.
This lunch after the first order period.
I feel bad for you guys.
I hope you're not too hungry. Are you all hungry? Not hungry.
Yes.
Okay, good.
Bad.
You got finger food, just start eating, so you get energy to press on. So for this question, you say fx, if you define function fx equals to cos x for x element from 0 to pi is a continuous function. So it's inverse. What's the inverse of fx?
F inverse x.
Which in this case is therefore cos inverse x is also continuous on its. What's the domain in this case of f inverse? How do I know? How do I find the domain of an inverse function?
Infinity.
To find the domain of the inverse function, we all have learned, the domain of an inverse function. Okay, let's continue the sentence. Enroll loudly and clearly. You know this, right? You all know this, right? Yeah. Okay, you know. Good. Okay, that's example 27. Okay, let's choose green color now to add color to our life. Okay, in the next section, it also tells you that if you have two functions f and g which are continuous, the derived function through some difference product division, they are also continuous. Of course, this one has a condition, that it mustn't be 0 on the denominator. Okay, and then, okay, you can read the small remarks about the proof, but what I want to highlight to you for the next couple of minutes is a very important result, This is a very important result in theorem 1.14. What it means is, for example, if you got a function fx, right? If fx is actually sine x, and then you have a gx which is equals to x squared plus 1, and you construct the function f of gx, and this function is simply sine of x squared plus 1. What this theorem aims to tell you is this: if you ever have to find the limit when x goes towards 1 of such a function, this theorem says because this is continuous, this theorem says I can bring in the limits. So the condition needed is for the function on the outside to be continuous. Then we can bring the limits. It's a very powerful result, right? That can use freely. And if this were the case, then it becomes sine of, in this case, is 2. This is what it means. Okay, now I would like you to try to use this. They're free period.
Probably.
So nice. So the partition is no good. The partition actually doesn't insulate sound.
It's like a cardboard. It's not a wall, it's cardboard.
Okay, let's try this question. All of you try this question. So this gives you what? The limit can be brought in, right?
And two ways to solve this. You either put the limit in or take the 3 out.
What do you mean take 3 out?
What is non-functional? Not log x cubed equals to 3 log x.
Oh, clever. Okay, sorry, I wrote only.
It's cubed. It's x cubed.
Okay, my bad. So this becomes ln of 8. Okay. Okay, then there's another result, This result is actually from the earlier one, So this result says if G is continuous and then F is also continuous at GA, then the composition is also continuous at X equals to A. And then the notes provided you with a short proof for this. Okay, let's pause a moment. So to prove that this is true, you will basically need to prove this line, You need to prove this line that when X goes towards A, F of Gx. By the way, this notation, are you familiar? f not g. If you read into the secondary school textbooks these days, they don't use such notation anymore.
I remember this was taught before. This was taught. Yeah, we used it at some point.
The reason why it was introduced is to distinguish between these two, you see.
There's a function.
This can be perceived as product. You know what I mean? But this means composition. However, written as like that, you have to understand this as the same as this, you know. You know what I'm saying? Yeah. So in the textbook that you see in schools these days, they don't have this notation anymore. They cut it off. But luckily we keep it because it makes it clearer. Okay, that you're talking about composite function. So because function f is continuous, by what we had just now, right? We can actually bring in could bring in a limit, you know. You can bring a limit and say that this is equals to f of limit and then because g is continuous at x equals to a, this becomes b. G is continuous, right, at x equals a, and we know that g x equals b. Right, then this one therefore gives you this one therefore gives you what then proof again? F. Okay, I think I've written too much. Let me backtrack. This gives you f of GA. Good enough. Okay, that's good enough. Right, like proving continuity of function, right? Finding the limit at x goes to a turn out to be evaluating the function, in this case the composite function, evaluating the composite function at x equals a. So when that's happened, we can conclude that the function fg is continuous at x equals to a.